Okay, hello everyone. My name is Mohammad Purhumayun. Hope you're all doing well. So let's get started. Today, I will start with a Python tutorial. Well, it's a brief review of SciKit, mainly scikit-learn library and how we train and test a machine learning model. So let's get started. Okay, so in this class, we use several, of course, Python is the main programming language for data science. We will work with several libraries of Python that are mainly designed for data science and machine learning and deep learning. You worked with some of them last semester, and we will continue working with them, and we will also work with some new frameworks and libraries and modules like Keras and TensorFlow and so on for deep learning. So Pandas is the first one, as you remember from last semester. It's a powerful library for processing of data. So most of the data that we receive and process, we convert that into data frames of Pandas data frames. So Pandas introduces at least two new type of data structure, series and data frames, and usually we convert or read our feature table as a data frame and work with data frames, which is very easy. So this is one of the very important libraries that we always use in machine learning. Scikit-learn is the main library for machine learning in Python that we work with that last semester. We will continue working with that for several algorithms that we had so far, but we will also work with other libraries this semester, and Keras and TensorFlow are the main frameworks that we are going to work with. Scikit-learn or sklearn, as you remember, it is flexible and it has a great documentation. So this is a very good thing about that. You always can find all details about all of those machine learning algorithms as well as some examples. And it includes optimal implementation of various classification, regression, clustering, and so on. For artificial neural networks and deep learning specifically, we will work with some more advanced libraries. But scikit-learn is pretty good for other machine learning models. So we know the process of training and testing, how to evaluate our machine learning models. I quickly review that in a few minutes. And I talk about cross-validation, and then we will go to Python to see some examples. So we know that we need to evaluate our machine learning model before using that in real life. Okay, so when you train your machine learning model on the training data, we cannot just trust it and start using that, especially if it's an important application. Like for example, medical applications. So we need to test it. But the problem is that the future data is not available yet. And that is why we need to split the past data that we already know the label of that into two parts, training and testing. So this is the idea, and this split should be completely random. We talked about this before. Scikit-learn does that for us. Usually in this case, sometimes like 70% or 80% of the data will be training and 30 or 20% will be testing. In some cases, when the data is very, very large, even this can be more, like 95% sometimes, when the data is huge, like millions of samples. In some cases, we have another data set here. So you can split your original data set into three sets: training, and then testing, and then validation. Okay. train, test, and validation. So validation usually used for adjusting some of the parameters of your model. So you train on this and then use another validation test to adjust, for example, the parameters of your machine learning model that we know we have some parameters for every machine learning algorithm that should be adjusted, and find the best parameters and then eventually test it on a new data set, testing set for the final report. So this is the idea. We did it several times in your homeworks last semester. We will do this again. We use training data to train your machine learning model. It is supervised, so we have both features and labels. If it is not supervised, again, we still have a training stage, okay? But we don't have label, we just have features. But in any machine learning algorithm, we always have a training stage. After you train your model, then we pretend that our testing data, which is originally a part of historical data, we pretend that we don't know the label, we test it on only features to make these predictions, and then we compare our predicted results with the actual labels to check the results, to evaluate our model. So this is a very classic approach to test your machine learning before using that in real life on future data. This is so important to remember. There should be no overlap between training and testing. Remember that. So training data, so in this approach, we assume that training data is our past data and testing data is the future data. So this is our prediction, this is our future data. We are not allowed to do any part of that in the process of training. So in other words, there should be no overlap between training and testing. As I mentioned, in some cases we can split data into 3 parts. Validation is the part that can be used to adjust the parameters. In cross-validation, well, this is probably a better, more fair way to evaluate your model. The problem with this splitting to training and testing is that although this is random, okay, so it should be random, you don't manipulate the data manually. It is completely random, but still maybe some samples that are difficult to predict or to detect or to classify happen to be testing set, okay? And then your results will be bad. Or vice versa. Maybe there are some samples that are easy to classify and they end up to be in testing set in this split, and then your results will be good. So if you repeat this process several times, of course, that would be better. So we want to repeat this splitting like 10 times and then use average of the results to make sure that this is fair. We can do that, but again, there is still a chance, even if you repeat that 100 times, maybe there is still some chance that some of the samples in the original data sets, they are never located in testing set, so we never test our algorithms in some of the samples. So this is the problem. So to make sure that we test our model on all of the on all of the samples here, we want to make sure that we test our model on every sample here. We do cross-validation. So cross-validation is a smart way of repeating this process in a way that we make sure that every sample will be used one time as testing sample, and other samples will be used, if we do k-fold cross-validation, other samples will be used k- times as training. So this is the process. we want to do k-fold cross-validation. So in this process, we split our data into k different partitions, okay, or k parts or k folds. And in the first round, round one, we used the first part of data, the first partition, as testing, and the other k-1 parts as training. We train and test our model, and it gives us some accuracy, for example, accuracy 1. In the second round, we use the second partition of data as testing, and the other k- parts as training. It gives us another accuracy, and repeat that k times until we have k different values for our accuracy, and the average of them will give us the accuracy of cross-validation, which is actually a very fair technique to evaluate our model. So some people can still argue that, again, this partitioning can be a little biased, or it can sometimes, it cannot be 100% fair. Well, that's right, but this is a pretty very well accepted approach in machine learning community. So everybody is okay with cross-validation. There is one more step to cross-validation, which is, it's very good to know that. It's very popular, especially in medical applications, in healthcare applications, when we want to evaluate the results. And in that approach, you don't randomly split your samples into k-fold. Sometimes we want to make sure that there is no data of, especially type of data, in both training and testing. So for example, suppose that we want to make a prediction for 100 patients, okay? For example, to predict something, to predict diabetes, okay, or to predict COVID-19 risk of dying. So this is, we published a journal recently in Elsevier, Journal of Smart Health, on predicting mortality rate for patients of COVID-19 using machine learning. So suppose that, for example, we have 100 patients, and from this 100 patients, from each one of them, I have 10 data samples. So, for example, I have 100 diabetic patients with diabetes, and I measure the blood glucose of them 10 times, each one of them, in 10 different days. So overall, I will have 1,000 data samples in my training set, okay, 1,000, because from each patient I have 10. So one approach is just to put this 1,000 data samples here and use regular cross-validation to split them in 10-fold, okay? But even a better way, which is very common in journals of machine learning in medical application, is to make sure that the data of a patient is not available in two different folds, okay? So in this case, we call it cross-validation, leave one subject out, or LOSO, okay? Cross-validation, leave one subject out. It means that rather than putting all of the data of this 1,000 samples together and split them into k-fold, we have 100 patients, so we leave one subject out and train on 99 patients, the data of 99 patients. We have 10 samples from each one of them, so we will have 10 data samples belongs to 99 patients, and one patient's out, so we have 10 data samples from this. We train on this and test on this, and then repeat that for next patient. Another patient's out, 99 patients for training, 1 patient for testing, another one. And we repeat this process 100 times so that all of the patients will be used as testing set. So this is called cross-validation, LOSO, or leave one subject out, which is even a better, fair approach for processing the data or evaluating your machine learning results. So you can open this IPython file, of course, in Jupyter Notebook. I will use 2 data sets to train train and test our machine learning algorithm for today. And the first one is a new data set that I want to use for diagnosing Parkinson's disease. And the second one is for cancer that I'm going to talk about later. So the first thing to do, of course, is to import the libraries that we need. For now, I just import scikit-learn. I want to use decision tree in this example. In your first homework, you will use random forest, AdaBoost, and XGBoost. Okay, so the first thing to do is to import the libraries that I want to use from scikit-learn. I import decision tree classifiers, NumPy, and Pandas. These are the standard libraries that we want to use. As I mentioned, for this example, I import a data set from UCI machine learning repository that I'm going to show you now. These are the information about this data set, and these are the 2 papers published on this. So UCI machine learning repository here, it's a very good database for some of the machine learning projects and data sets. It's of course much smaller than Kaggle, but you can find some interesting project here. So if you come check it here at archive.ics.uci.edu, so these are the list of data sets that you can see. Many of them are medical. So if you are interested in medical project, you can see a lot of medical projects and data sets here. They are all machine learning. Okay, so they are all data sets for machine learning. And it gives you some information. For example, this is a classification problem, number of features, number of what type of those features are categorical or integer or whatever, heart disease, hepatitis, many different projects. Okay, even iris is here. So I use this data set for predicting Parkinson's disease. So this is a data set. You can see the information of that here. It includes 23 features, and the data set is about 200 data samples. And these are the information about features. If you are interested, you can check it out. So there are 23 features. So the first one is the name of the patient, which is of course coded. It's encoded for the privacy, and so we don't use that. It's not actually a real feature. The other 22 features are mainly, the details are here, are mainly the test results of a vocal test that the patients take, and the results are here. They are numerical values, and the goal is to detect if this person has Parkinson's disease or not. Okay, so this is the data set. I directly read it from the machine learning repository using read CSV from Pandas and put it in a data frame, Pandas data frame. So if you see the data, it looks like this. Okay, so these are different patients. This is the name of them, which is encoded, different features, and there is one column here, a status, which is the label. Okay, if it is 1, it means that the patient has Parkinson. If it is 0, it means that the patient does not have Parkinson's disease. You can always read the columns of a data frame using this attribute.columns, and so I use some of them as features here. I don't use name, and I use status as the label. And the rest of them I use as features here for my machine learning model. So run. Status will be the feature Y, and my decision classifier, I define it. I notice that I defined a random state value. I fixed this because if I want to repeat this algorithm, I want to get the same results. There are some randomness in every machine learning algorithm. For example, initial values the algorithm select. So you can fix this so that every time it selects the same initial values. And then using fit, we train our machine learning algorithm, very simple, on this data set. So again, I use decision tree classifier. You can use any other machine learning model you want. So after this line, your machine learning model is trained now. So your decision classifier is built and trained, and now it is ready to test. So it's ready to predict actually. So I provide my machine learning algorithm with 2 new samples. So these are 2 new patients, for example. This is the data that we collected them during the test, and sample 1, sample 2, I put them in a list and provide it to the trained machine learning algorithm that I have, and the method predicts, will make prediction for me. 1 and 0 means that the first patient, this guy, has Parkinson's disease, but the second patient does not have Parkinson's disease. So pretty straightforward, but now I want to evaluate our model. So I do both splitting and cross-validation. So these are pretty straightforward. We had most of this last semester. For evaluation, I split the data into training and testing, and train, test, split function that I imported that from SciKit will automatically do that for us. This one tells me that I used 30% of the data as testing, and so 70% of the data as training. As you see, it creates X train, X test, Y train, Y test for me. If I run it, if you see the size of each one of them, 136 samples will be 70% of the data, which is training, and 59 samples will be the testing data set, which is 30% of the original data. Now I only train my machine learning algorithm on training data. Here you go, X train, Y train. I provide both of them because this is supervised learning. Train, and now I test it on testing data. By testing that on testing data, this is the prediction results. So as you see in prediction part, I only provided the features to the algorithm, no label. These are the results, and now I can compare the accuracy of my model by comparing these prediction results to the actual value that I have from here. Okay. To compare that, I import this function again from scikit-learn, accuracy score, and it gives me the accuracy of 91%, which is not bad, right? which is pretty good. I can compare the actual value versus my prediction for these patients one by one to see to find the mistakes, right? If I do this, it shows all of them, but I just want to print the samples that I predicted incorrectly. Okay, so this is what I print result. So I first make this result data frame. It's a new data frame. I put actual and prediction, actual value and my prediction as two columns of that side by side, and then this is what I want to predict. This table, these data samples where the actual value is not equal to the prediction, only print those lines. Okay, this is using pandas data frame, a very Pythonic way to just in one line to show me the samples that are not equal with no if else conditional operator. So these are 5 samples, 5 patients that I misclassified. Okay, and 91%, not bad. So this was using the regular testing, splitting to training and testing. Okay, so I continue with cross-validation. As I mentioned, in cross-validation we repeat the process of training and testing several times so that we make sure that all samples have been used as testing. To do that, again, scikit-learn has functions for that. So cross-val score, I import that, and then here I defined my decision tree classifier, and this line of the code and this command cross-val score, it's a very useful function, very helpful. So rather than you manually split the data 10 times into training and testing and do for each one of them, each time in each round you train and then test and then save the results and repeat again in a for loop, well, one single command does everything for us. So scikit-learn, it made everything very simple for us. And so all I have to do is that this is my cross-val score. I just provide the machine learning model that I want to try. I defined it here, I put it here as an input of this function, and then the entire data set. This is not testing and training anymore. The entire data set, feature part and label part. CV equal to 10 means cross-validation is 10 means I want to do 10-fold cross-validation. And in each round, the number that I wanted to report is the accuracy. I'm doing classification here. You can get other values as well if you want, but here I want accuracy. If it was regression, for example, in regression case, you could get mean square error, for example, or negative mean square error, not accuracy. These are the results. Okay, so it tries 10 different times because this is cross-validation, 10-fold cross-validation, and it gives me 10 different values for accuracy. So as you see here, they are very different, right? So this one, my first try, so first try was this, right? This one, when I use the first fold as testing and the rest of them as training. It gives me the accuracy of 95%. But look at this try, for example. This try it gives me the accuracy of 52%. So it seems that there are part of data that was really difficult to classify. Okay, so this is a problematic part. It was a little bit better than random guess. So these patients in this set was mainly the patients that the algorithm made mistake for, maybe most of them. And so these are 10 different values. As you see, by changing the training and testing the data, the results will change a lot. That's why cross-validation is a fair approach. And then average of them. Average of this 10 values will give me accuracy about 80% for predicting Parkinson's disease in these patients. Okay, so let me continue. Again, these things are just a review, very quick review of the training and testing a machine learning algorithm that we had from before. So in this tutorial, I want to show you some other metrics to evaluate your machine learning model. So you remember that a very big problem with many machine learning models in real life is that actually this is a very common problem, and the data set is not balanced. Okay, so our data set is not balanced. So for example, when you want to predict earthquake, okay, if you collect the daily data, or especially when you want to predict a disaster, or in medical applications when we want to predict a emergency situation, for example heart attack or something like that, so the data is highly unbalanced. So maybe this is the data set that you have, and maybe 1% of that is positive and 99% of the data is negative. Okay, so predicting cancer, 1% of that is positive, 99% of that is negative. And remember, every machine learning algorithm is based on a cost function. That cost function gives us some kind of error in prediction. Okay, and the machine learning algorithm tries to minimize that error, that cost function. So for a case like that, your machine learning algorithm will learn that if it always say no, if it always says no, then it still get the 99% accuracy because it is right in 99% of the time. And usually when you provide a data like that to your machine learning algorithm, this is what we get. So be careful. If you see like 99%, 98%, 95% accuracy for a data set, don't get too excited too early, because in many real life projects and data sets, this is the case. And in fact, our machine learning model completely misclassified this part, which was actually the main part of the data. This is important. Okay, this is not important. This 1% was the part of the data that we really care about and we want to detect. This is the patients with cancer, for example. This is the earthquake that happened. So this 1% is something that we want to predict. So this, you train a machine learning that it gives us very accurate results, but it doesn't work at all. That is why sometimes we don't use accuracy as a metric. And last semester we talked about that. We saw some other metrics such as false positive rate, false negative rate, and we plot ROC curve. So it kind of measures the sensitivity of your model, how well your model can predict a positive sample alone. Okay, so in that case, you just focus on that 1% and check your model to see how well it detects that 1% of the data. So this is what I want to talk about and review. Before that, I also want to talk about the probability. Sometimes we don't just want to predict a yes or no, but we want to predict the probability of an event, probability of earthquake, or probability of rain for tomorrow, or probability of cancer. I start with logistic regression. Logistic regression, as you remember, is a classifier that can also give us the probability of an event because it's based on the idea of regression. To use that, I import several libraries, okay, several modules from SciKit library, and also pandas and NumPy as always. I use Matplotlib for visualization. Okay, so please feel free to check this out. Matplotlib is a great library in Python. If you want to do visualization in Python, Matplotlib is one of the best libraries that let you plot everything you want on different types of graphs and visualization. Of course, we just talk about the data science, machine learning part in this class, but generally this is an ideal library in Python to plot something. So for this example, I import another medical data set. So you see a lot of medical data sets in my examples because medical applications and healthcare applications is my favorite field in machine learning. I read it from our GitHub page for 4662. This is the data set that we want to use for predicting breast cancer. And in your first homework, you use the same data set. It includes 9 features that I imported here. And these features extracted from a type of medical image. So suppose that you have an image, a medical image like MRI or CT scan or ultrasound or other type of X-ray image, and we extract these medical features from that, and then we want a machine learning model to predict or detect or diagnose if this patient has cancer or not. Okay, or in other words, to see if this tumor is malignant or benign. Run it, and here I split the data into training and testing, similar to what we have done. Split, and then regression, logistic regression. This is where I define my logistic regression model, and training on training, tested on testing, and then accuracy calculation. This is what we just did. So this logistic regression gives us the accuracy of 93%. Well, not bad, but for an application like predicting cancer, of course, we prefer the better accuracy. So now, as you see here, our prediction for these patients are 0 or 1. Okay, but sometimes, in most of cases, we want to see the probability of these events, not just yes or no. So this method predict probability, it gives us the probability of the event, and it is not actually anything new. So logistic regression is based on a linear regression method, which in fact it predicts the probability first anyway, and then compare it with a threshold to make it binary. So for example, for the first patient, the probability of cancer was 9%. And then the algorithm compared that with a 50%. Because it was less than 50%, it returned 0. For second patient, the probability of cancer was 99%, and then it compared that with 50% and it reported 1. Okay, so by default it compares that to a threshold, which is by default it is 50% or 0.5, and by comparing this probability to that threshold, it creates zeros and ones. So this is the idea. But the fact is that for an application like this, we want our machine learning model to be much more sensitive, right? Because we don't want to miss anything. So we can reduce this threshold rather than like 50% threshold as a cutoff value for our making decision if this patient has cancer or not. We can reduce that to like 10.1 and compare anything which is above 0.1. We raise a red flag for that patient, mark it as 1 so that we can do other procedures or exams or examinations or other tests, further tests to see if this patient has a cancerous tumor or not. So in fact, we reduces this threshold from 50% to like 20% or 10%. This way we make our machine learning model more sensitive. Okay, in fact, we increase the true positive rate of that, but at the same time, because you make your machine learning models more sensitive, you will generate a lot of false alarms. Okay, so false positive rate will be also high. So to make a better understanding of this model and have more flexibility to work with this model, we can try different thresholds. So we can use like 10 different thresholds, starting from like 5% and then like 10%, 20%, 30%, 40%, 50%, all the way to 90%. Try different thresholds and make, for example, 10 different models with 10 different sensitivities. One of them are very sensitive, one of them are less sensitive. 10 different machine learning models with 10 different sensitivities, and then check for your application which one is best. This is what we do here. In fact, this command does this for us, all of those things. So so I import that from metrics. This is my machine learning predictions for probability, these results. Okay, these probability results that I just created, I provided to this function, and this function compare that with different thresholds for me and generate different results for me, and creates, based on that, compare the results with the actual value and creates different false positive rate, true positive rates for me. So when I run it, this is the results. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, it just created 10 different machine learning models for me. Okay, the first one, this one, is not sensitive at all. Okay, but this one is very sensitive. That is why if you see, this is false positive rate. Okay, this is false positive rate. FPR is false positive that I print here. For the first one, the false positive rate is 0. It means that it does not make any false alarm because the model was not sensitive at all. But for the last one, the false positive is 100%. It means that the model was very, very sensitive and almost detected everything as positive. So 100% false alarm. So none of them are ideal, but we want something in between. And this is true positive rate. So the first model, because it was not sensitive at all, it didn't detect any true value. It didn't detect any true positive. That's why this value is 0. But these models right here, for example, this model right here is a pretty good model because it detected all of those positive samples. The false alarm was about, I think it's this one or maybe this one, about 15%. So look at this point, 15% false alarm, 100% detection. That is an ideal point. Okay, this is a great point for selecting your machine learning model for this specific application. Let me plot this. If I plot this, it will be more clear. Let me plot the curve. So this is the curve that I plot using Matplotlib. So this is my data. Okay, so this is true positive rate versus false positive rate. Okay, so at this point, at this point right here, your model is very sensitive. You detect all of those cases, but you also generate 100% like false positive rate. So this is not an ideal case. But look at here, right here. At this point, you give 100% detection, so you detect all of those patients with cancer, but you also generate 15% false alarm, which is okay. 15% false alarm for an application like that is okay. So this point is an ideal case for your machine learning algorithm. So I select this as an operating point. Okay, so this is what we do. And as I mentioned before, this blue line is random guess. So your curve should not come below this. And the area under curve, all of those area under this red curve, is a metric that tells you how well your machine learning does. 95% area under curve is pretty good. AUC, area under curve. You can do it. You can plot it this way. And I use here, I use Matplotlib, import Matplotlib as PLT, and just plot this graph. This is very important. So these things are important because when you want to design your machine learning algorithm, this is so important to select an operating point for your application. Maybe there is another application that is still 15% false alarm is huge. Okay, so remember that if we want to, for example, predict earthquake for people of Los Angeles and evacuate the city of Los Angeles based on those predictions, 15% false alarm is huge. It's gonna be very, very costly. We cannot make 15% of times we make generating false alarm and evacuate the city of Los Angeles based on this, right? This is very high. So in those cases, we still have to reduce the sensitivity of the model. So to compare two different models, I create another model. In this model, I intentionally reduce the accuracy of my model by selecting only 2 of the features. I only make prediction based on 2 features. So this is going to be a less accurate model. It gives me 88%. Because I want to plot 2 curves in one graph to compare them. So look, these are the 2 graphs that I have. As you see, of course, the area under curves give me the overall performance of each model. So the closer to this corner, the better. So the red one is better for most of this part. Maybe for this area, the green one is better. Okay. So these are 2 different classifiers. But for this application, because I want a very sensitive model for medical applications, this point right here that gives me the 100% detection, 50% false alarm is ideal. The green one, if I want to get 100% accuracy, I have to select here, which is also 100% false alarm, which is not good. Okay, so the red curve at this point is an ideal operating point for this application.